So today we are going to start a new model that is called as logistic regression. Now, why regression? Why is it regression? I will tell you. So initially people did this linear regression kind of thing, like mathematicians came up with the linear regression stuff, that given a data point you can fit the data and you can predict something, right? So linear regression was something like this. You have data points x, y, and you are basically fitting a line over it or fitting a curve over it or whatever it is. Now the same concept people said that can we use this concept for classification problem? Like this is regression, where you have a data point
Okay.
from the same domain and you are basically fitting a line. Now people said that if we have data from two classes, suppose two domain, say one is this domain and say another is this domain. So if I perform linear regression onto it, I will be, getting some line like this, right? If I perform fitting function on this data, I will be getting maybe, uh, some line like this, right? Which tries to fit the data as it best, right? But people said that no, I don't want regression here. Basically the objective here is to classify these two data points. So can I find a line or a curve? Like linear regression, you have two things. You can fit a polynomial also, or you can fit a single linear also. So can I find a line which can separate these two classes? So that line will be like this. So at the time when linear regression came up, people came up with this logistic regression also. So the idea was same, that we have to fit a line, but the word fit is not, I mean, appropriate here, because when we use a fit, it means fitting over the data. So that fitting over the data is regression. Here they wanted to fit a line, but what they wanted was that it can classify the data points. So it was a kind of fitting, but not for the purpose of prediction, not fitting on the data, but it was like a placing a line somewhere so that the classes can be, separated out. So they named it logistic regression, because they thought this is also some kind of regression. Like we were fitting a line in the linear regression, similarly we are trying to fit a line here, so they call it regression. But regression term is a misnomer here. It's a misnomer here. People always confuse between them, and a lot of people you will find that they will think this is kind of a regression, but it is not a regression. Basically, the name should be logistic classification. Okay, but anyway, at that time the mathematician named it logistic regression, so people are still following the same name, logistic regression, but actually it is a classification technique. So I hope you can differentiate between the objective of these two models differently. Here the objective is, in here the objective is to fit the line, and here the objective is to classify the data points. Okay, so you have,
Okay.
yeah, so you have two classes and you have to identify between the data points. You have to classify the data points. Now just again one more example. Suppose these were the data, right? And again, suppose this was again some data. So, initial what people said, that what we will do, we will fit a line over the data points only. We will do linear regression directly. Basically, we will do linear regression only, but we will try to find a threshold. So what I will do, I will try to find a threshold. Suppose this threshold I found. So I will say that above this threshold will be one class and below this threshold will be another class. With linear regression only people tried initially. But they found that when I am taking the uh, threshold above threshold, when I am taking the value above threshold, all these points are coming, right? And below threshold also points are coming from the both the classes. So then this didn't work. So then actually people came to this conclusion, the mathematicians, that no, this won't work. We have to, instead of finding a line like this and putting a threshold over there, what we should do is we should find a line which can form a boundary over that, so that now on one side there will be one class and on the other side there will be one class. Okay, so now for finding this boundary, the mathematician, the people, they proposed a different hypothesis, a different model, you can say. So if you remember, what is the regression model? Linear regression model. Linear regression model is theta naught plus theta 1 x, right?
X. Yes.
Or polynomial regression, if you ask me, I will write something like this: theta naught plus theta 1 x plus theta 2 x square. Or you can add more terms here, but yeah, like this. Now, logistic regression, they said that I have to somehow find that line, instead of fitting the data, I have to find that line which can somehow, I can say that, okay, if this is this side, I am going to say class A and this side class B. So they thought that the model should be something which gives me a value between 0 and 1, and I can clearly say that if the value of the regression, or of the data point, the model, if the value is greater than 0.5, I will say it as a class B, and if it is less than 0.5, I will say it class A. Okay, so just try to understand this. People said that you use linear regression only. You use linear regression only, but this value, the predicted value, somehow I have to map it on a scale of 0 to 1, so that if this value becomes more than a particular threshold, say 0.5, it will give me 1, and if it is less than 0.5, it will give me 0, 0 class. So like that they said. So now what can be a function? What can be a function which can, transform or map this regression value between 0 to 1 with this scenario? So, in mathematics there is a function called as sigmoid function. What is the function name? Sigmoid function. So the model of logistic regression becomes this LR is linear regression. This is different. This is logistic. Okay. Maybe I will write it again. This model is logistic regression. I will tell you. This is logistic regression. Okay. So there is a function in mathematics, sigmoid, and in that function, if you pass this, function, suppose this sigmoid function is some function, we don't know what is sigmoid, just assume that this is some function in which when you pass theta naught plus theta 1 x, it gives you a value between 0 and 1. And if it is more than 0.5, I will say it class A. If it is less than 0.5, it is class B. Good enough? Now let us see what actually logistic regression do. Logistic regression. Okay. Now, logistic regression basically plots a function like this. See, this is 0.5. This is 1. This is 0. Now, basically, what I am plotting is, okay, I did the wrong thing. This is 0. This is 0.5. And this is 1. This is basically, this y-axis is basically my logistic regression function. Logistic regression function value. The hypothesis of logistic regression. I will write HL. HL theta naught. HL x I will write, okay. So linear regression from now on I will represent it like this in mathematics. This is linear regression, and whenever I have to represent logistic regression, I will represent it like this. Theta is hidden, okay, in logistic regression representation. So this is just a representation I have assumed to make for this session. So this is this, and now whatever your data point is, I will simply do the regression only like this, but I will transform this value through a function like this. Through a function like this. So it will saturate at 1, it will never go beyond 1, it will never go like this, it will never go beyond 1, it will be something like this. So this is basically your 1 and this is your 0. So no matter how big your value of this goes, it will saturate here, and here there will be a curve, and then it will again saturate on this side. It will saturate on this side. So this is minus infinity and this is infinity. And you know what is on x-axis? On x-axis it is basically this thing, h of theta x. So whatever data point you got, you do the same thing as regression, but just pass it over this particular function. So suppose you got a theta, suppose you got this regression value theta naught plus theta 1 x as say minus 10,000. So where is your minus 10,000? Somewhere here. So on this function, if you will, on this graph, you will say it will come here. It will come here. So when it is coming here, basically it is less than 0.5. It is less than 0.5 because if you see on this axis, it will be somewhere around 0. So I will call it as class 0. And suppose your theta naught plus theta 1 x value comes out to be say 200. So 200, if you go on mapping here, say here it is 0, here it is say 10, 20, like this 200 says they come here. So 200, if you will map on this graph, it will come here, somewhere near to 1. Somewhere near to 1. So this will, so above 0.5 I will call it class A, and below 0.5 I will call it class B. This is a kind of mapping logistic regression does. And the graph which you are seeing, this graph in mathematics, it is they call it a sigmoid function. Which function? Sigmoid graph. If I on Google, if you just type sigmoid function, you just type, you see this graph will come. This is a sigmoid function, this one, this function. So you see, if you go on more than 0 towards infinity, it will always have the value, it will always carry the value more than 0.5. And here they have shown it, they have touched this one line, but actually it never go beyond this, it will always be near 1. And this side, no matter how much negative you go, it will never go beyond this line. It will always be near 0, max 0 it will go. So it basically, it scales down the value between 0 to 1. And if it is more than 0.5, I will say class A, and if it is less than 0.5, I will say class B. So if I conclude from this, if the logistic function, if the logistic function is greater than 0.5, I will say my y is equal to 1. If h of logistic regression x is smaller than 0.5, I will say y equal to 0. So this is basically the criteria of logistic regression. Now people said, can you define this logistic regression in terms of linear regression? Because ultimately, to calculate this formula, to calculate this hypothesis, you are using linear regression only. So people said, can you convert this into linear regression? So yes, it can be converted. How? If the linear regression value is greater than 0, or I will write it something like this, if it is equal to positive, then my y will be 1. If my hypothesis value is negative, y will be 0. So same thing, same model I am representing in two ways. One through linear regression, another through logistic regression. But the logistic regression, the funda here which goes is, it is like this. This function, whatever it comes, whether it is coming positive or negative, maybe a small positive number or a very big positive number. So whatever it comes, this will be transformed through this function. I'm not able to make it properly though. This function, and then you will get this. Now you may say that what this function is actually is. How do you transform this? Just an example I will tell you, a very simple example. Suppose I have this data point. This example which I am telling you, it has nothing to do with logistic regression or linear regression. I am just telling. Suppose you have a 1D data point like this. Now I say that this is a 1D data point. If I say transform it through this function, what you will do? You will project this data point here. You will project this data point here. You will project this data point here. You will project this data point here, and you will project this data point here. Now, what is actually the meaning of this? Visually, for understanding purpose, it's fine that you are saying that you are projecting, but what is this? This curve is basically a parabola. We usually study this in our school, maybe 8th or 9th class. You know, there are four kinds of parabola. So,
Yes.
So basically there is an equation of parabola, y equal to something like x square minus 4bc, something like that. There is equation. So whatever
Yes.
the x value is, you just, whatever this value is, whatever these values are, one by one you place it into x, and whatever the b and c coefficients are there for this curve, you put it here and you will get the y. So you will get this data, the projected data. Good enough? So
Yeah.
similarly, this example I have just given you to show that how do you say this the same thing here, that for understanding purpose it is good that this is what this is x, theta x is what, this is basically nothing but theta naught plus theta 1x, right? So how are you
Yes.
transforming this thing through this function? How are you transforming into this? So what is this function actually? What is this sigmoid function? This sigmoid function is 1 upon 1 plus e. E is basically exponential. That value 2.33 is there, you remember exponential? So 1 upon 1 plus e raised to the power minus this linear regression value. This is the sigmoid function. Like I told you, the parabola equation is something like this. Similarly, the equation of sigmoid is something like this. Maybe I will make it again. This value, whatever you go get here, this value will take to this, and which is basically 1 upon 1 plus e raised to the power minus theta naught plus whatever equation. This is just a linear regression. This is a linear regression. And then this value which comes, you just make it e raised to the power minus this. Good enough?
Okay.
Now we will
Okay.
analyze this function mathematically. We will try to analyze this function mathematically. So, let's say you had some data points and you calculated this h theta x is equal to theta naught plus theta 1x. Okay. Now this value comes out to be a positive value, a large positive number. So this is a positive number.
Yes.
Basically, this will become what? This will become 1 upon 1 plus e raised to the power minus and then a very large positive number, right?
Yes.
So this value will become what? This whole value. E raised to the power minus a very big number, say 100. What it will be? This you can write it as 1 upon e raised to the power 100. And you can write this as 1 upon 2.33, whatever it is, raised to the power 100. Which is a very big value. This value will be very big. So this value will reduce to 0. 1 upon a very big value will be what? 0. I mean near to 0.
Yeah. Near to.
Near to 0. So if your this x theta plus theta 1x sorry, theta naught plus theta 1x, this linear regression value, if it is very big, so then this whole value e raised to the power this big number will reduce to 0. So 1 upon 1 plus 0 will be what? 1.
1.
So that is what only we have seen right now. That if in this function, if you see, if your linear regression value is a positive number, a big positive number towards this side, this is 0, here it is negative, here it is positive. So if it is a positive number, this it will lie where? Near 1. So if it is a very large number, the value of this sigmoid function will become 1. So that 1 means it will basically, if it is a very large number, we'll say here, it will correspond to 1 on y-axis. Understood?
Yeah.
Now again a new thing, I mean again the same thing. Suppose this is there. You first you remember this function first. It is very important to see the function. This is a infinity positive and this is positive negative. Now on the y-axis we have 0 here and we have 0.5 here and we have 1 here. And when we say when the value is more than 0.5, I will say class A. If the value is less than 0.5, I will say class B. And the function goes like this. So suppose this is 1. So the function will go like this. This is your logistic sigmoid function, right? Now I said if you have a very big positive number, it on this graph it will lie somewhere here. So it will be equal to 1. I have also shown you mathematically how it is coming 1, right?
Yeah.
Now just check for when your theta naught plus theta 1 x comes out to be a huge negative number, a big negative number. Let's see what happens. This thing becomes a very big negative number. Means on x-axis it is lying somewhere here, a big negative number. Okay? So when this is negative, what happens is, you just see how the equation changes. So if suppose this number comes out to be a very negative number, big negative number. So now this thing is basically a negative number which is lying over here. So what happens is this becomes 1 upon 1 plus e raised to the power, a big positive number it will become, isn't it? Negative.
Yeah.
There was already a negative and this is also negative. So negative will become positive.
Positive.
So now this factor, if you will see, this will become 1 upon 1 plus, say 2 raised to the power 3, 2.33 raised to the power say 100. So that will become a very huge number, like 10,000 or something like this. So now this whole number will tends to 0. I mean this will become 1 upon a very big number, na?
Yeah.
So it will tends to 0.
Yeah.
So when it tends to 0, how you can see it graphically is, see this is a very big negative number. So if you see the y-axis, it will be near 0.
Near 0.
Near 0. So this is another case. See, this is class B. So mathematically we have seen now that how this function can help me doing the classification. So this function, I mean, I must say this, that this function, which is also known as sigmoid function, this is also known as sigmoid function. This particular function is a very popular function.
Yes.
So this particular function, I must say that this particular function is a very famous function, also called as sigmoid function. Okay, and this particular function can map your linear regression value between 0 to 1. So and it can help you in classification problem, where if the value is more than 0.5, we will say class A, and if it is less than 0.5, I will say class B. In the terms of linear regression, if you want to hear, it will be like, if it is a positive number, if it is a positive number on this side, it will always lie on this side, so it will always be greater than 0.5. If it is a negative number, it will always lie on this side, which will be always smaller than 0.5. So it will be a class B, 0. Okay. And
Okay. Okay.
this sigmoid function, you will find that it is very popular, and this is a basis of, the whole neural network. That is why logistic regression is very important if you are learning, if you are going for deep learning. If you are going for neural networks, understanding neural networks are made up of, various logistic units, various logistic neurons. So this particular algorithm which we are seeing is a very basic one neuron problem, or say one logistic function, which does a two-class classification for you. So it only does two-class classification. This you will agree with me, right? Because there are only two things. Depending upon the hypothesis value, whatever it is coming. If it is coming, so I will maybe write it once more. If your hypothesis value is coming more than 0.5, you will say class 1. If the hypothesis value is coming less than 0.5, you will say class 0. Good enough? Now, and same thing you can talk in terms of linear regression also. If it is greater than 0, basically a positive number, I will say, when it is positive, it is basically greater than 0.5. That sigmoid function will become greater than 0.5. So it is class 1. And whenever it is a negative value, I will say it is a class 0. Good enough? So is
Yes.
this is basically what is meant by logistic regression. So people named it regression only because, still linear regression was involved, and people thought that it is just an extension of linear regression, where we are trying to map the linear regression values between the scale and in 0 to 1, so that we can do the classification, that if it is more than 0.5, I will say it class 1, or if it is less than 0.5, we will say class 0. Like everywhere, this thresholding kind of thing is there, like if you get more than 50% number, you will be called as pass, and if you get less than
Yes.
50% number, you will be called as fail, right? So similar kind of
Yes.
classification the logistic regression does. But actually, if you see uh, the theta naught and theta 1, actually what the boundary which you are making is a line only, right?
Mm-hmm.
The boundary, this theta naught and this theta 1, with this theta naught and theta 1, you are basically drawing a boundary only. But only thing is, this theta naught and theta 1 value will be tuned such that it will not fit the data like this, but it will fit a data like this. So the scenario has changed. The process of finding theta naught and theta 1 is similar, but only thing is the objective function has changed. The objective function, the error term That error term has basically changed now.
Okay. Okay.
Because the earlier the objective was you have some data points and you are trying to fit a line over this. So the objective was to pass through most of the data point as best as possible.
Minimize the error.
Yes, to minimize the error. So you had the objective was you have to find the theta naught and theta 1 so that it can pass through most of the data point and the error is minimized. That cost function, you remember what was the cost function for linear regression?
Yeah. Yeah. Summation of y actual predicted y actual square.
Yeah, this was the function, right? So this was the function
Yes.
for linear regression. Now try to understand this point. This was the function for linear regression because you had to minimize the error. You have to minimize the error so that this line can best fit to this data point. Now with logistic regression, our objective has changed. With the two class data points, my objective is not to fit this data and pass through the data points as best as possible. I am not going to use the similar cost function like linear regression. This cost function I am not going to use at all here, because this cost function will be used when you have to pass a line, something like this, where you have to fit the data so that as best as possible it goes through the data points. Here the objective is to find, see, in both the cases, in LR and in logistic regression, both the cases you are finding theta naught and theta 1 only. Both the cases are the optimization function only, where is the optimization problem only, where you have to find the best line. But with linear regression, the best line is which passes through all the data point. With logistic regression, the best line is which divides the data such that you can get the zero, that funda, that if it is 0.5 greater than 0.5, it's this class. If it is less than 0.5, it is this class. So the
There is
purpose
no
is,
concept of
yeah, what?
so there is no concept of minimize the error
There is
in
a
logistic.
concept of, no, there is a concept of minimizing the error, but that error definition will change.
Okay.
The error definition, this error definition won't be applied in logistic regression. A new error function will come. This error function is called what? Do you have an English term for
Mean
this?
square error.
Huh?
Mean square error. Mean
Yeah,
square
yeah,
error.
yeah. Very good. This is called as mean squared error. So this error term is called as mean squared error. With logistic regression, there is another error which is actually minimized, so that you get a line which classifies your data point instead of fitting it. The objective has changed, so the error will also change. And there is a very fancy name for this. That name is called as uh, cross-entropy function. Cross-entropy function. This is this is called as cross entropy, or sometimes it is also called as entropy loss. You can maybe search on Google. Cross entropy loss. This is an error for logistic regression. So like we had an English term for this, we have an English name for this, which is called as cross entropy function. All these names are just fancy names. Don't be afraid of these names, or wherever you see, you will be hearing lot of fundebaji, a lot of terminologies in machine learning, but they are simple concepts only. The point which I am trying to make here is, you must understand this, that in the linear regression, first of all, you must understand this in the both the cases, in the linear regression and the logistic regression. Both the cases, the funda is to find the theta naught and theta 1. So you are basically finding a line. But now the second step which you have to understand is, in linear regression the objective was totally different. There the objective was to fit the data point as best as possible. So you have to pass the line through the data point. Here we have to find a line, but we have to find that theta naught and theta 1 which can discriminate between the two classes, which can discriminate between the data point, some data point and another data point. Some data point from class A to the data points of class B. So that type of theta naught and theta 1 you have to find. So now let us come to, so all these things which I have conceptually and I have told you, this is all about linear regression. Now I will directly come to, see, the hypothesis representation of logistic regression is this. You see this one. This one. This is the function basically. So this is the hypothesis. If you remember the hypothesis, the same slide, if you see linear regression slide, the hypothesis representation was something like this. This function you are seeing, na? This is for logistic regression. For linear regression, we would see something like this.
Theta 0 plus theta 1 x.
Yeah. So this we used to see. Okay. So basically our this thing has just changed. The function has been changed. And this actually, if you see, this hypothesis of linear regression has been used here. Okay. That's the same hypothesis which has been transformed here. Okay. So anyway, so that's one thing. But I am not going to go for this. What I wanted to show you is something else. This is the same thing. I mean, you can just see the same linear regression term you are passing through this sigmoid function. Here, this is your sigmoid function. You see, this G is defined as this. And this Z is basically nothing but this thing. Good enough?
Okay.
Now, decision boundary and all fine. Yeah, decision boundary and fine. So similarly, one thing I just missed to tell you, if similarly, like in linear regression, what was happening, you had to fit a line, right? If you have something like this, so if you have some data point like this, you are fitting a line, right? But if the trend was something like this, if your data points are like this, so what were you fitting? You were fitting a curve, right?
Curve.
So similarly, and you were fitting the curve with this kind of equation, polynomial equation, right? So in logistic regression also you can put the same hypothesis in that function. In this function, you can put this z, basically the same polynomial hypothesis you can put, and you can, instead of drawing a line, you can draw a curve also. You understood what I am trying to say?
Okay.
I will again maybe explain you. So in linear regression, if you had points like this, what we used to do? We used to place a line like this. Similarly, in logistic regression, if you have some data like this, you will try to place a line like this. Again, another example, in linear regression, if your data points are like this, you will fit a polynomial to this, right? Like this, maybe degree 3, this is degree 1, right? So
Yeah.
this is theta naught plus theta 1 x. This is theta naught, this is degree 3, remember, theta 1 x plus theta 2 x square. Now it is degree 3, so I have to make one more term, theta 3 x 3, x to the power 3, right? So similarly, this kind of curve also, this hypothesis also, you can use the polynomial hypothesis in logistic regression. So suppose you have one class like this, and you have another class like this. Now can you draw a line which can separate these two classes? Tell me, can you do can you somehow, can you make a line, a straight line which can classify these two classes? No. So
No, multiple
using,
line.
yeah, using this polynomial curve function, you can make a boundary like this. So inside the boundary, this is class A, and outside the boundary, this is class B. This also you can do with logistic regression. This, see, I told you, like in linear regression, there is something called as linear regression, and then there is something called as polynomial regression. So similarly, I can say there is something called as logistic regression, and there is something called as polynomial logistic regression. I mean, there is no such term like polynomial logistic regression, but I'm just for understanding purpose, I am just making that term. So this is like a polynomial, a logistic regression model using a polynomial hypothesis, right? And this is simple logistic regression using linear regression hypothesis, and this is linear regression hypothesis, and this is polynomial regression hypothesis. Are you able to differentiate between them?
Yeah. Yeah.
Okay. So that is great. Maybe once you will revise this thing, maybe you can see that. Maybe you can hear them this session, recorded session, and you will get more. I mean, you can revise it also, because a lot of concepts are there and lot of things
Yes. Yes.
they are coming, but then it is very logical. And if you just take pen and paper, and if you will write the equations, the mathematical equation, you are really going to enjoy. I mean, it's actually very interesting, although it may seem boring, but if you deep dive into it, I mean, you will certainly enjoy this. Yeah, but so the purpose, I was actually trying to tell something else. Uh, I will come back to this slide because this is a new thing which I saw. So I just yeah, this is the thing which I wanted to tell you. So I told you, again I will repeat my stance. The linear
Okay.
regression and logistic regression, in both the cases we have to find the theta naught and theta 1. Basically we have to find the line. But the objective is totally different. In linear regression, you are trying to find a line which fits your data completely, and in linear regression, and in linear regression, basically you are trying to fit the data point, and in logistic regression, you are trying to find a line which can separate your data point rather than fitting it. So
Okay.
both have a different objective. So the error function, the error term, the cost function of linear regression, which was mean squared error, that mean squared error was meant to find the error between the predicted and the actual, I mean the line fitted and the data points basically. So if the line is fitting the data points closely, the error will be less. So our objective was to minimize that cost, isn't it? So that is why the mean squared error was used there. But in logistic regression, how can you use that error? You cannot use that obviously, because you are not fitting your data point. You are not fitting your training data. You are trying to find a line which can separate them out. You are trying to find a line which can do this thing. You are trying to find a line which can do this thing. Right? So now the purpose here is, what is your cost function? What is the error term here? Let us see the error term. Let us analyze the error term. So if you remember, one more thing, just one more thing I will tell you. In linear regression, if you will remember, in linear regression, in iterations, if you see the iterations,
Yes.
and here is your cost function. So what was happening? Suppose I started from this cost function. So what will happen in iterations? It will go down, 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 down,
Reduce.
and at one point of time you will find that now the cost error is not changing. So you will say now stop at this iteration, because my error is not decreasing further. You remember gradient descent algorithm we have seen.
Yeah. Yes. Yes.
Or you start from this place. If you start from this place, you will come down, down, down in iterations. I mean, now the iterations are going like this. So you will come down, down in iterations, and maybe after some iteration you will saturate, and so they will say like this. So that basically what I mean to say is, in linear regression your cost function was a ball shaped, right? When you take a mean square error, you start from here, you will go down, down, down like this, go down, and you will find the minima. You will find the minima. Or you start
Okay.
from this position, you will go towards the tangent, towards the gradient, towards the negative gradient, and finally you will reach to the minima. Fine. Now, if now people said, do you think people have not tried linear regression, this mean squared error with logistic regression? You know, initially people tried mean squared error only. Although the logic, although the objective is completely different. In linear regression, you are fitting your data point. In logistic regression, you are trying to find a line which can separate your data. But you know, initially people couldn't come up with the loss function, the error function, the cost function. So they tried this one only, mean squared error. So you know how the error was behaving, how the cost function was behaving with mean squared error in logistic case. It was behaving something like this. It was a curve like this, but it was lot more fluctuating,
Okay.
like this. It was a non-convex problem. In
Why it is so?
because the objective is completely different, right? This sigmoid function, you
Hmm.
see, this sigmoid function. This
Hmm.
sigmoid function, when you are mapping through sigmoid function, basically here in this particular example, if I say, in this particular cost function, how are you calculating this? You are calculating through this theta naught plus theta 1x,
Theta.
right?
Yeah.
And then you are subtracting it. So this worked well with this, because it was a convex function. So convex function,
Hmm.
it is easy to minimize, right? Through gradient
Yeah.
descent, gradient descent you can minimize it. You will always find if you go the negative gradient, I told you, like theta naught will be updated like theta naught minus alpha, and then something like this, right?
Did.
So it will be negative gradient. If you will take, you will always go down, go down, go down, go down. But in logistic case, using the same error function, when they actually put, instead of this, they put something like this, sigmoid of this thing. So
Okay.
this is a non-linear function. I told you, no, this is something like this. So because of this mapping, this problem became a non-convex problem, and so this error term was discarded. This error term was no more valid, and they said that no, this is bullshit. I mean, we cannot go with this error function. Okay.
Okay.
So this is just they tried plotting it and they found it like that. So uh, so logistic regression cost function is this basically. Now they have
Hmm.
to come up with a new function. So I will now, with a fresh page, with a fresh mind, just try to understand this. This is the cost function of logistic regression. Actually, this regression sessions, basically linear regression and logistic regressions, this basically regression sessions are a little bit more mathematical. Actually, machine learning started with mathematics only. So the initial models they came up with, linear regression, logistic regression, and these things, whatever they proposed, they were highly mathematical. You will find this machine learning course little comfortable when you go ahead. After this logistic regression, when we will come to the supervised classifier portion, there you will find some, we will start with some classifier which will be easy to understand, and there will not be lots of mathematics involved. Of course there are mathematics involved, but that will be at least understandable. That's, I think so. Let us see what happens. But yeah, so somehow you understand this, invest time on this, whatever days are coming, you invest time on this, and go through this. So later on you will find it good enough, easy enough. And this is also very interesting. I mean, once you go in this, you will find it very interesting. So, cost function linear, this logistic regression, I am going to write because that cost function, a mean squared error cost function was not working. It was a non-convex problem. So this this cost function they call as cross entropy function. Like mean squared function, this is error function. So what is this function? Let's see. Hmm. This function is basically this function. So given the theta and the whatever y value you have, the cost function will be simply uh, if y is equal to 1 and if y equal to 0. So, you know, I told you in supervised learning problems, you will also have levels, right? For the training data, you will
Hmm.
know that whether it is of class A or class B, you will have levels. So this is the level. So this becomes minus log of h theta x, and this became, I think, yeah, log of 1 minus h theta x. So if y is equal to 1, this will be the case, and if y equal to 0, this will be the case. Okay. And then when you actually plot this, you will find that if you will plot this graph, you will find that this is basically a convex function. So this particular function worked very well. And that's why they went with this cross entropy function. When they plotted this function, if you will plot this function, you will find that on this side, suppose you have the cost function, and on this side you have iterations. So in iterations, whatever it was, they find that this is so like even you go like this or you go like this. They found that it was a convex function. Okay, actually this you may have questions that how are you making this like this? I mean, how are you making this a convex shape? So
Yes.
this has actually to do with the log property. If you see the logarithmic curves, log x, say, this log x, can you see this is a convex problem?
Yeah.
So this is a convex thing. If you see like this is a convex thing. So it starts from here and goes here. And if you see, basically here it is not log x. If you see, one is log minus log x, it is actually. So minus of log x is a gradient, right? See?
Okay.
So same function I am making here. And if you will see, minus of log 1 minus x, minus of log 1 minus x, it will be just from the opposite side, it will be there, like this. See? This is the curve it is making there. So for this, when y equal to 0, when y is equal to 0,
0.
you will get a curve like this. And when y is equal to 1, here, you will get a curve like this. Now, you may have questioned that how is this curve coming? So, for that I would suggest you try different values of x. So just try x1, x2, x3, x4 and try to calculate the value of log. I mean, this is a logarithmic curve.
Yeah.
I mean, it will be hard if you will ask me how this curve is coming. So again, I have to explain, I have to maybe make a table for different value of x and what is this minus log 1 minus x, what is the value coming, and this thing I have to show the plot, and then you will be convinced that this curve will be like this. So let's not go to that much detail of plotting this function. This you can try on your own, right?
Okay.
You can just try minus log x. Just try. Make a table like this and say take different values of x and take their log value and just try to plot it. You will get something
Okay.
like this. Okay. And I mean, you don't need to, and I mean, okay, that's fine. I mean, I also go very much into mathematics, but you don't need to go through all those things, because anyway, while implementing the Python, you will be using the sklearn logistic regression. So that particular library will take care of this. But yeah, mathematically, you should understand this logic. So, like, of course, we are in an IT job or we are in the industry, so we don't need to care about these mathematics because we have some library which is doing things for me. But when you suppose you are applying for some research job or you are applying for PhD somewhere, like people do, they will then that committee for selecting you as a PhD candidate for their US universities like maybe Stanford or MIT or whatever it is, they will dig deep into this and they will ask you these questions. But yeah, a corporate guy, I don't think they will go to logistic regression this detail. But anyway, you just need to understand that this is the cross entropy function which is used for calculating the error of logistic regression. One question, definitely a legitimate question you may ask, that why are these two values? Why is if y equal to 1 this is this, if y equal to 0 it is this? In linear regression it was nothing like that. It was just one formula. In linear regression it was just one formula.
Hmm.
So in linear regression I had only one y and it was just one formula. Why are you here, always telling that y equal to 1, y equal to 0, then this, then this? Because linear regression is a real valued predictive model. There is only one y, there is only one class. In linear regression, there is only one class. Suppose if I take the example of amount of heat generated. Now, depending upon the feature, you have to just predict what is will be the amount, the number of what will be the amount of heat generated. You don't have to classify things. So there was only one thing, one class. Here, in this particular case, you have now two classes. So you have to make the error part, you have to make separately for both the classes, isn't it? So that is why
Yeah.
the error for y equal to 1 is calculated like this, and the error for y equal to 0 is calculated like this. Maybe I will make it again. If y is equal to, I will also just look at where is that PDF. Okay. Yeah. So y equal to 1. Okay. So if y equal to 1, the error will be considered as minus this one. And if y is equal to 0, it will be considered as minus log 1 minus x. Sorry, this is not x actually. This is the linear regression model actually. This is now what? This is what? This is basically the logistic regression model, right? Okay.
Okay.
So this thing we have seen calculation. So this thing will be applied here, and 1 minus n and this. And log, why do we take log here? You will ask me that how is this log coming in linear regression where there was nothing like log. So log basically we are taking just to ensure that the cost function become a convex problem, because this slant is basically minus log x, and this slant
Hmm.
is basically minus log 1
1
minus.
minus 6.
So that is why we are using log. And you see, it's very interesting. If you are on this side of the cost function, it is y equal to 1. If you are on this side of the function, it is y equal to 0. So for both the classes, if you see, the convex function will be same. So either you start from this point or you start from this point. You have to minimize this cost function and find out at minima what is your theta naught and theta 1. And that theta naught and theta 1 will define a boundary which will actually separate your data points. Good enough?
What if there are 3 data points?
3 classes you mean to say.
Yes, 3 classes.
So it do not do anything. I mean, it cannot do that. Logistic regression as in the basic form, or you can say logistic regression fundamentally is a binary classifier.
Okay.
It can only divide between 0 to 1, because I told you na, this particular function, where is that? This one. If this particular logistic regression, if it is greater than 0.5, I will say class 1. If it is smaller than 0.5, I will say class 0. So there is only 2 classes. Okay?
Okay.
Because you see, you remember this function?
Hmm.
This side there is only from 0.5, this side there is class A, and negative side there is class B. So it's a 2 class
Yeah.
classification. I mean, logistic regression people also use it like multiple logistic regression classifier they will train, and they will try to use it for multi-class classification also. I mean, if you have 3 classes or if you have 4 classes, you can do it with logistic regression, but only one logistic regression will not do, will not
Okay.
serve. So you have to train, maybe if there are 4 classes, you may have to train maybe 10 to 12 logistic regression classifiers, and then using those models you can maybe classify. That's again a different case altogether. But fundamentally, the logistic regression classifier is just a binary classifier. It is.
Okay.
I mean, I don't want to overwhelm you as of now, but yeah, multi-class classification can also be done, and there are other models also. Like we will see a model called support vector machines. That model is also fundamentally it is a binary classifier only. But you can do again with lot of support vector machine models. You can use it for multi-class also. But let's not take those cases, because those cases will overwhelm the things. I mean, again, you have to see a lot of classifiers being trained, and then so there are different models basically which can do multi-class classification very easily. Okay, so we usually in multi-class classification we use them, not these logistic classifiers. For binary classification, it is very good. Okay, so we have also seen the
Okay.
logistic, the cost function, the error function for this, right? But
Yeah.
also, yeah. So this one we have seen for this, when y equal to 1, you will get this slant. For y equal to 0, you will get this slant. Now what is this written?
Simplified.
Simplified cost function. So you remember you said that in linear regression we had only one class function, this cost function, mean squared error. Here we are making it two different criteria I am putting. One criteria is this, and then another criteria is this. But the point is, if I am talking about error, I am saying what is the error of your model. Tell me what is the error of your model. In linear regression, you will give it a value. You will tell a value that the error of the model is something 500, 10,000, or 0 or 1, something like that. You will just one value you will say. But in logistic regression, when I will ask what is the error of your model, what is the cost function of your model, so then you will not say him like this, no, that if y is equal to 1, my error is 500, and if y is equal to 0, then my error is 400. You will not say like that, right? You have to come up with a simplified number, one number. Just one number you say that, okay, 500 to 500. Okay. So basically now I am going to, we are going to transform these two different criterias for y equal to 1 and y equal to 0 in just one function. In just one equation which will be written in this box, I will fulfill both the criteria. How can you do that? Any idea? Anyway, I mean, of course, right now you cannot have idea for this, but yeah. So I will tell you, I will go like this: y log h of l x. See, I have multiplied this y into this. I have done nothing new. I have just multiplied the class with this. And then minus, sorry, yeah, plus 1 minus y. So this part I am making it for this first criteria. And now this part I am making 1 minus y into log 1 minus this one. So this part I am making it for this one. Second criteria. Okay. Okay. So this is
But
the,
how,
yeah.
How you can convert this y equal to 0 in 1 minus y?
Yeah, I will tell you. I will tell you. See, if suppose if my y is equal to 0, what will happen? This whole term will become 0. Y
Yes,
is 0.
yes,
This whole term will become
yes,
0. So what will be remaining? This y is 0.
yes,
So 1 minus 0 will be just 1. So you will be left with log 1 minus this, right?
yeah,
And this is what your criteria was. This was your criteria, right?
mm,
This one.
yes,
So I can write it like that or not? Now if y equal to 1, let's say the one scenario. If y equal to 1. So if y equal to 1, this y equal to 1, this whole term will go 0.
yeah,
If y equal to 1, so 1 minus 1 0 and 0 multiplied by this whole thing will become 0. So only
yeah,
thing you will be left with, and this y is again 1. So 1 multiplied with this will be the thing. So this will be what? So now what has this become? This is satisfying the first criteria.
yes,
So if y equal to, whether y equal to, if y equal to 0, then still this problem, this whole equation will satisfy this purpose. And if y equal to 1, still this same equation will satisfy the criteria. So with a single equation I am satisfying both the criterias.
okay,
Do you understand this?
yeah, yeah,
So now I am making a simplified means only one cost function. Whatever you want to write, you can write here. Okay, fine. So the cost function goes like this. Good enough?
yeah,
If you just evaluate it for y equal to 0 and y equal to 1, you will get the same equations. When y equal to 0, this whole term will go 0. This whole term will go 0. So it will become minus, and this y is again 0. So it will become minus log, fine. And when y equal to 1, this 1 will be 1. So this will become minus this. And y equal to 1, so this is basically 1. So 1 minus 1 is 0, so whole thing will become 0. So this is the scenario. Good enough?
yes,
So basically, finally we have arrived to an error objective. So I will repeat my the stance which I made earlier, that finally you have to find the theta naught and theta 1 value only. But in linear regression, the theta 1 and theta naught can easily be found by minimizing the cost function, which was a mean squared error. Why mean squared error? Because there the objective was to just pass the line through as best as possible way through the data points, so that the error is minimum. But in the logistic regression case, you have to find the line only. You have to find the theta naught and theta 1 only, but you have to find it that line which can separate your data y equal to 0 and y equal to 1. So you have to, so the same objective of fitting the data points will not work here. I also told you that the cost function becomes non-convex in that case. If you use mean squared error only, it will become non-convex. So we use this logarithmic technique, because with the logarithmic function which I showed you, that's a convex function basically. We will always come towards minima. So that particular function we take in logistic regression case. And finally, we have simplified both the criteria into just one function. This, see, yi into log of this I plus 1 minus y into log of this. Now, both the places here were actually minus. So this minus I have taken out here. Okay. So this both has become plus now. And minus is outside. And then you calculate this term basically. If you see, yeah, you calculate this term over all the data points and you divide it by all the data points. Similar to what you used to do in linear regression.
Yes.
Similar to what we do it in linear average. Basically, I have to give the average cross entropy. So, see, in this n number of points, suppose you have n number of data points. Let's say you have 100 data points. In 100 data points, 50 points where there will be y equal to 0, and 50 points will be there where y equal to 1. Just an example I am telling. If you have 100 data point in training data, maybe just 50 will be 0, class 0, 50 will be class 1. So, I am just summating over, I am summing it over those 100 points. Wherever this y will be 0, this thing will evaluate. And if y is equal to 1, the data point where y is equal to 1, this thing will get evaluated. But whatever is evaluated, one of the terms will be evaluated. I am not bothering about what is getting evaluated, but whatever will be evaluated, I will just keep on summing it. So I will keep on summing errors of all the data points, and finally I will divide it by 100 to get an average error. Agreed? Hello?
Yes.
Yeah. So,
Yes.
agreed, right? Basically, if your x is 100 data points, out of 50 are of class A and 50 of class B. This is training data, okay? This is training data. So when I will calculate the cost function, I will go from in to I1 to n, and I will divide it by 100. I will n equal to 100. And for the 50 data points of where class A was there, I will say class A 1 and I will say class B 0, say. So I will do that y into, this is a negative here, so y into log x, sorry, log of h lx, and then plus 1 minus y into log of 1 minus h lx, right? So this whole thing I will evaluate. So for all the 50 data points which were 1, this thing will be evaluated only. And for all the data points which are class 0, basically this becomes 0. So this whole thing will be neglected and only this thing will be evaluated. But whatever is evaluated, for all the 100 points I am adding them up. And then finally I will, from the sum I will divide it by the n and I will get the average entropy loss. Average or average cross entropy loss. That's the.
You need to sum of class A and class B, both of classes.
What? Come again?
Do you need to sum of class A and class B and take an average of both of classes?
Yeah. So see, this single function is doing both the things. This function only See, when the data points are of class A, when the data points are of class A, only this thing will be evaluated, right? Because the y
Yes, yes.
value will change. Y value will change for the classes, right? The y value will be 1 for class A and y value will be 0 for class B. So one of the term will be evaluated, isn't it?
Hmm.
So,
Yes.
so this is basically the cost function, and this is how you actually calculate the J cost function, the error term basically. Okay, in this
Okay.
PDF you see this is how you calculate. Okay, and the see. So you remember what was gradient descent in linear regression? Start at random theta naught and theta 1, right? Then calculate or say plot cost function, and in loop basically this thing will come in loop only. In loop just update your theta naught and theta 1, isn't it? And then you also keep on checking whether the previous cost function minus current cost function is greater than some threshold epsilon. If it is greater,
Epsilon.
then keep on updating. If it is less than epsilon, then just stop. This was the gradient descent, right?
Yeah.
So the same gradient descent will work in the logistic regression also. Only thing is this plotting of cost function. This cost function will change. This cost function has become now this. This cost function has now become
Yes.
this. Whatever we have seen, no, that. So this cost function you will now plot and it will again
Hmm.
become a convex problem. The gradient descent remains the same. Okay.
Okay.
So that is basically the point it is showing. See, this is the gradient descent. This is the cost function, and if you see, this is how the similarly like linear regression, the thetas will be updated, because I told you you are finding the theta naught and theta 1 here only, similar to gradient descent, similar to linear regression. So same thing will be acted, uh, and this partial derivative of, if you see this partial derivative of cost function. So earlier we were using this partial derivative of cost function, whatever it was there, it comes out to be something like this, right? Predicted minus actual, and then into x. Something like this was used to come, right?
Yeah.
For theta 1, for theta 1. For theta naught, for theta naught, the partial differentiation comes to be like this, multiplied by 1, isn't it? So similarly, the same partial derivative, the partial derivation of you, if you do this for this function, it comes out to be the same. So nothing is changing basically. The same derivative function is used here also. Okay.
Okay. Okay.
See, can you see this? Only thing is the same thing is used here, like your cost, your predicted minus actual into xj, but only thing is this cost function is of logistic now, so it has become this now. this function is basically calculated for gradient descent. Okay.
What about alpha? Alpha value?
Alpha is basically that learning rate, na? So if you see the cost function of logistic regression will also be like this. For this function, if
Mm.
you plot, this is also a convex problem because of log we have seen. So
Okay.
now whether to take a big steps, so to prevent overshooting, this alpha is used. I told you this alpha we will keep it as 0.01, so that if this cost function is very a large number, it won't allow it to overshoot like this. It will when you multiply a very small number with a large number, it will minimize that, and it ensures that you are going slowly towards the minima. And once you reach at the minima, you will stop. Good enough?
Yeah, good.
So so what I will do, I mean this completes the whole logistic regression. Okay. The whatever things we have seen in regression, the same thing we have seen in logistic regression. We have understood what are the sigmoid function and all. This is advanced optimization. This you do not need to know. These things you do not need to know. That's fine. So basically, this sums up our logistic regression part. But what I will do, I will like whatever this session has gone. In next session, I will make a quick revision again tomorrow. We will have a
Okay.
quick revision for 15 minutes. I will send you this
Okay.
recording